Hello, everyone. This video and the next will be about diagonalization of matrices, which is a procedure to go from a certain square matrix to a related diagonal matrix. We'll see why it's important and we'll see how it's done. Before we move on, I want to remind you of the notion of similar matrices. We've already seen it in a workshop, and here is the definition. We say that two matrices are similar, A and B, if I can write one as PBP inverse, so if I can squeeze the other between a certain invertible matrix and its inverse, just as it's written here. Here's a little example. We have a pair of matrices A and B, and I claim that they're similar with respect to the matrix P. First of all, observe that P is invertible because its columns are two vectors that are linearly independent. And to check that they're similar, we can perform the following check. Rather than computing P inverse, to check similarity, you can take the definition, A equals PBP inverse, and multiply both sides by P. Then P inverse and P cancel each other out, so the only thing you need to check is that AP is equal to PB. Let's check that. -2, 1, -2. That's A. If I multiply it by P, I get 3, 1, 1, 1. And the result is 2 by 3, 6, -3 is 3. 2 minus 3, it's -1. 1 minus 2, sorry, 3 minus 2 is 1. And 1 minus 2 is -1. Let's compute PB. 3, 1, 1, 1. That's my B, sorry, my P, and B is 0, -1, 1, 0, 0, -1. Multiply these together. Well, multiplying this matrix by the vector 0, 1 extracts the first column. So, and multiplying the matrix P by the vector 0, -1 extracts minus the second column. So we have a match. In fact, A and B are similar, and the similarity matrix is P. Why is similarity important, and why is it important in particular for us right now? The key point of similarity is that similar matrices have the same characteristic polynomial. Let's try to convince ourselves of this feature. If I have two similar matrices, A and B, I can write them like this. So when I look at A minus lambda I, well, A is P, B, P inverse minus lambda. Here I'll write the identity as P identity P inverse, because P identity P inverse is nothing but P times P inverse, which is equal to the identity. So I can substitute this in for the identity. P identity P inverse. But then it means that on this right-hand side, I can use the distributive law of matrix multiplication and factor out a matrix P. So I get B P inverse minus lambda I P inverse, all multiplied on the left by P. And I can factor out a P inverse on the right in the same way. So B minus lambda I times P inverse. Okay, so A minus lambda I is P times B minus lambda I P inverse. In particular, the determinant of A minus lambda I is equal to the determinant of P times the determinant of B minus lambda I times the determinant of P inverse. But the determinant of P times the determinant of P inverse is 1. So we get that the two characteristic polynomials, the polynomial of A is equal to the polynomial of B. Having the same characteristic polynomial means that you have the same eigenvalues with the same multiplicities, because both eigenvalues and multiplicities are determined by the characteristic polynomial. We are interested in this fact especially when one of the two matrices is diagonal. In the example we looked at above, B is a diagonal matrix, which means that it's really simple to compute its eigenvalues. The reason why that's simple is that, well, for a diagonal matrix, I can just subtract lambda here to write B minus lambda the identity, and the determinant of B minus lambda the identity is just 1 minus lambda times minus 1 minus lambda. So the eigenvalues here are lambda equals 1 and lambda equals minus 1. However, by similarity, since we know that A is similar to B, we know that the eigenvalues of A also are plus or minus 1 with multiplicity 1, without having to compute the determinant of A minus lambda B, which is a little bit more complicated than computing that of B. Hopefully this convinced you that it's important to know when a matrix is similar to a diagonal matrix. And that's such an important notion that we have a name for it. And we say that A is diagonalizable when it is similar to a diagonal matrix D. So diagonalizable matrices are the ones that can be written as AP equals PD for some invertible matrix P, or A is equal to PDP inverse for an invertible matrix. So the importance of diagonalizability, I've already mentioned one of the factors, which is if a matrix is diagonalizable, it's easy for us to compute the eigenvalues. But it's easy to work with diagonal matrices in general for all sorts of computations. Here's an example. Suppose I want to compute my matrix A. These are the matrices from before, A and B. I want to compute A multiplied with itself 10 times. I could do that by just sitting down and patiently computing A times A times A times A times A times 10 times, or I can compute B to the 10th, and diagonal matrices just raise their entries to the 10th exponent. This is a property that it's not true for other matrices, but if it's diagonal, then the exponent carries over to every one of the single entries in here. So B to the 10th, in this particular case, is equal to the identity. And then if I were to compute A to the 10, I can exploit the similarity. For example, for A squared, I would get something like this. A squared is PBP inverse squared, which is nothing but PBP inverse times PBP inverse. But now I have a P times P inverse in here, which is a copy of the identity. In other words, A squared is nothing but PB squared P inverse. In the same way, I can just write a longer chain of these when I compute A to the 10th, and I find that A to the 10th is P times B to the 10th times P inverse. B to the 10th is easy to compute. We did it. It's the identity. So A to the 10th is P identity P inverse, but P identity P inverse is just a copy of the identity. So that's how much simpler things become when you're allowed to take advantage of diagonal matrices. So the next questions in order are, if I give you a matrix, how do I know when it is diagonalizable? And if I know that it is diagonalizable, how can I find the diagonal matrix D and the matrices P that diagonalize it? We'll start from the second question. And the next video will instead be dedicated to the first one. When is a matrix diagonalizable? In the next example, we'll try to use what we know to see what must happen for a matrix to be diagonalizable. So our goal in this example will be, given a matrix A, to try and diagonalize it using the information that we've known so far, or trying to figure something else out. So when I say that we want to diagonalize a matrix, I mean that we want to find the matrices D and P such that A is equals to P times D times P inverse. The one thing we know is that the diagonal matrix here is similar to A, so it must have the same eigenvalues. So the first thing that we should compute are the eigenvalues of A. Finding the eigenvalues is a matter of computing a characteristic polynomial, which is nothing but the determinant of 7 minus lambda, 6 minus 1, 2 minus lambda. When we compute this determinant, we get 7 minus lambda, 2 minus lambda, plus 6. And let's clean it up. We get lambda squared minus 7 lambda minus 2 lambda plus 14 plus 6. That's lambda squared minus 9 lambda plus 20. And this seems to factor into lambda minus 5 times lambda minus 4. In other words, the eigenvalues of A are lambda 1 equals 5 and lambda 2 equals 4. So my diagonal matrix will be given by, well, for a diagonal matrix, the eigenvalues are the entries on the diagonal. So D must be 5, 4. Okay, now the next step is to learn something about P. So we only know that it's a 2x2, so its two columns are going to be a couple vectors, v1 and v2. Let's see if we can learn something about those vectors. If I multiply, so what we want is that AP is equal to PD. So if I multiply A by P, that's the same as writing the matrix whose columns are AV1 and AV2. On the other hand, if I compute PD, that's the same as the matrix V1, V2 times 5, 4. And if you compute this product, that's nothing but 5V1 in the first column and 4V1 in the second column. In other words, for these two things to match, what we need is that AV1 is equal to 5V1 and AV2 is equal to 4V2. This is just another way of saying that V1 and V2 must be eigenvectors of the matrix A. That's exactly the definition of eigenvectors. Now, the last thing that we need to be careful about is whether the matrix P that we are finding is going to be invertible or not. Invertibility of P depends on whether the two eigenvectors V1 and V2 are linearly independent, or equivalently, whether they are a generating set for R2. So the summary in this 2x2 case is that to diagonalize a matrix, we must have that the diagonal matrix similar to it has eigenvalues into its diagonal entries, and the columns of the diagonalizing matrix must be eigenvectors for the corresponding eigenvalues. This is something that needs to happen. However, it may be that P is not invertible. When P is invertible, or in other words, when V1 and V2 do generate the whole set, the whole space R2, then A is a diagonalizable matrix. Let's state the same result in general, and then we'll see an example of it. So a general result, so in the n by n case, the matrix A is diagonalizable if and only if the eigenvectors of A are a generating set for Rn. Equivalently, there is a basis V1 through Vn of Rn of eigenvectors of A. So I can collect eigenvectors so that I can find a basis between them, And if I can find the basis, then A is diagonalizable. The diagonal matrix D will be the one that has eigenvalues on the diagonal, and the diagonalizing matrix P will be the matrix whose columns are vectors V1 through Vn. Let's apply that theorem in one example. We wonder whether this matrix here is diagonalizable. In other words, what we want to do is to find a basis of R3, in this case, of eigenvectors of A. So our initial goal is to find a basis for R3 made of eigenvectors of A. Because that will guarantee that A is diagonalizable. To find eigenvectors or to find the matrix D, the first thing that we need to do is to find the eigenvalues. This is the usual computation. You check the determinant of A minus lambda I, and you set that equal to 0. If you do a few computations, which I encourage you to double check, you get that your characteristic polynomial, the determinant of A minus lambda I, is this polynomial here, so that we have 3 eigenvalues, -5, 2, and 3. So our diagonal matrix will have entries like so. Maybe I should point something out. If A is diagonalizable, it's not diagonalizable to just one matrix. In other words, I could pick a different order for my eigenvalues. So I can pick a different order of the lambda I, and that is no harm, but the important thing is that I reflect the same order in the columns of P. We'll see what I mean in this example. What we'll do here is to find an eigenvector for lambda 1, an eigenvector for lambda 2, and an eigenvector for lambda 3. So the important thing is that P contains these eigenvectors in the correct order, in the order that matches the fact that we have lambda 1 up here, lambda 2 in the middle, and lambda 3 at the bottom. So as long as you make your choices consistently, the order doesn't matter, but it needs to be respected. Okay, let's find the eigenvectors corresponding to these eigenvalues. For lambda equals -5, let me bring the matrix down. Our goal is to compute A plus 5 times the identity. And that becomes 3 plus 5, that's 8. We get a 5 here, there was a 0, and then -3 plus 5 becomes a 2. Now, to find eigenvectors in here, I want to, as usual, solve the associated linear system. So I will do that by doing a reduced row echelon form. And I can add the first row to the other two to eliminate a few things. If I add it to the second, I get 0, and then here becomes 7 minus 7. And if I add it to the third, I get 0, 0, 0. This is not quite yet the row reduced echelon form, I can divide the second row by 7, so I get 1 minus 1, and then I subtract that from the first row. So this becomes 0, 1, minus 1. The first row, when I subtract twice the second, is 8, 0, 0, 0, 0, 1, 0. But then I can divide this by 8 and get a 1. That's my reduced row echelon form. So when I look at the solution set to the homogeneous linear system, this will be my free variable times, well, let's see, 0, x1 has to be 0, x2 is equal to x3, and x3 is free. In other words, v1 corresponding to lambda 1, which is minus 5, is the eigenvector 0, 0, 1. Now I picked lambda 2 to be equal to 2. So let's compute the same thing with the eigenvalue 2. Again, we look at A minus 2I, and this is the matrix A. So you have to do 3 minus 2, 0 becomes 0 minus 2, and minus 3 minus 2 here. When I clean those up, I get 1, minus 2, and minus 5. Okay, again, let's do some reductions. We want to solve the associated homogeneous linear system. So, well, let's see, the first and third row are identical. So I can just erase one with the other. Now I can just add 8 times the first row to the second, and I get 1, 2, minus 2. I get a 0 here. Then I get minus 2 plus 8 times 2 is 16. So that's a 14. And then I get minus 5 minus 16, which is minus 21. Now I can keep simplifying things here, and I get that this is 2 minus 3, or rather, I should divide further. I divide everything by 14, so I get 3/2. 0, 0, 0. And I use that to eliminate the first. So I get a 0 here, and here I have minus 2 times 3/2. So that's, I believe it's a minus 5. Yeah. Okay. Wrapping this up, we get that the general solution here is given by x3 times x3 has coefficient 5 in x, and it has coefficient 3/2 in x2, and then it's a 1. So in other words, I can set my second eigenvector to be 5, 3/2, 1 by solving the associated homogeneous linear system. Now let's do the third, which is 3. Our matrix A is right here. When I take A minus 3 times the identity, I get a 0 here, I get a minus 3 here, and I get a negative 6 down here. Again, let's do a row reduction. When well, the first row becomes 1 minus 1, like that. And then I can subtract the third row from the second, and I get 0. Then I have minus 3 plus 2, that's -1, and -5 plus 6 is equal to 1. And then the last row, I can flip the signs, 8 to 6. I can do an extra step, and what I get is I bring the third row up, and I divide it by 8. And then I can use the second row added to the first and get a row of zeros. And then the other row that is remaining is 1 minus 1. Okay? So far, so good. Last step here is 0, 1, minus 1. I take a fourth of the second row and I subtract it from the first. So here I get 6 over 8 minus a fourth minus 1. So it's 6 over 8 plus a fourth. That becomes 1. In other words, my third eigenvector is going to be given by the solution set of the homogeneous linear system attached to this matrix, which is, as usual, it has a free variable x3, and it will have a 1 here, and then it has -1 and 1. I'm looking at the coefficients here and flipping the signs, and then the 1 down here is for the free variable. So V3 is equal to -1, 1, 1. Now, let me double check I didn't make any mistake. Okay, let's resume the recording. I double checked that there wasn't any mistake. In fact, there was a tiny mistake here in lambda 2. V2 was before written with a 5 in the first entry, but it actually should be a -1. Everything else should be all right. Okay, so now the conclusion of our reasoning here is that we found the matrix D and the corresponding matrix P. Now observe that to the eigenvalue lambda 1 corresponds V1 here, and to the eigenvalue lambda 2 we put V2 right here, and to the eigenvalue lambda 3 we put the column V3 here. It's important that the order of the eigenvalues appearing is the same as the order of the columns inside P. Now, we should check that P is invertible, and in fact, that can easily be done by computing the determinant. We can even do it now. Maybe let's compute the determinant using a cofactor along the first row, which is plus minus, so it's -1 times the determinant of, I erase the central column, 1, 1, 1, 1, plus -1 times the determinant of the matrix 1, 3 halves, 1, 1. Now, the determinant of 1, 1, 1, 1 is 0, because the columns are linearly dependent. So we get -1 times 1 minus 3 halves, which is 1 half, which is different from 0. So P is invertible indeed. Okay, let's stop here. And next time we'll think more about getting more detail about understanding when a matrix is invertible or not. We'll refine our latest result.